Our next presentation will be from GlobalFoundries, and our speaker will be Hiren Majmudar. He's a VP and General Manager for the Computing Business Unit at GlobalFoundries. You may have heard that they've developed some specialized process technologies at GlobalFoundries, specifically for AI acceleration, and Hiren will be discussing those with us today. So welcome.
Very good. So following up on all the wonderful discussion about new AI architecture, let's talk a little bit about how to convert those architecture and ideas into silicon. Pleasure to be here on behalf of GlobalFoundries team. We'll talk about why we believe that designing smarter and not smaller is the call of the day for AI chips going forward. So let's first quickly start with a market analysis done by ABI Research. If you look at the annual AI silicon TAM, it clearly shows that we can divvy up AI silicon into, broadly speaking, 4 categories. CPU and GPU, as well as FPGA, has been playing a front and central role in general purpose compute and now into AI. But starting a few years ago, lots of research started happening into AI silicon. People call it ASIC, people call it AI accelerators. As you see today, end of 2020 will be shy of about $3 billion in the AI silicon, but AI silicon or AI accelerators are going to see significant growth. And one projection shows that by 2024, from about shy of 3 billion, that market is going to get close to $9 billion. No wonder you see significant number of startups pursuing all sorts of AI accelerators, as Linley highlighted in his keynote this morning. And we expect many more will come about as we move forward. We are pretty excited about what we are doing at GlobalFoundries with many customers that we have announced, and we'll talk about that in a second. Let's quickly take a look at the history. If you look at the general purpose compute, last 30, 40 years, we have been pretty blessed that year after year, generation after generation, we saw significant advance in power performance efficiency of what CPU did, and then what GPU did, and what FPGA has done. But as cloud and other technology advances really gave birth to pushing the CNN based AI accelerators, I think the demand in terms of improvements of both TOPS and TOPS per watt really eclipsed, and we really needed 100x to 1000x improvement, and that's what AI accelerators have been able to do. And we will show you some examples with what our customers have achieved in this space so far. Now, briefly speaking, if we look at Dennard scaling, which in 80s and 90s, and we talked a lot about it. It was all about power density, and a few years ago, basically Dennard scaling became dead, as we all know. But lately we know that Moore's law is also challenged as we go forward, right? And historically, Moore's law yielded 40% reduction in transistor cost. But as we go look at 7 nanometer to 5 nanometer, that benefit is just barely about 10 to 15%. And, transistors were getting smaller, and clock speed was a pretty significant benefit that we derived from scaling. Now, if we go look at going from 7 to 5, that benefit is expected to be just about 10%. So future is going to be for those bold companies that are willing to try new architecture, new techniques, new types of purpose-driven compute, as we know. And Linley covered this in the morning, that you are going to have database processing, specialized AI chips, high performance computing, and many more innovation that's on the horizon as we see and as we will see going forward. At GlobalFoundries, we offer 2 broad platforms. One is our 12LP and 12LP plus FinFET platform that delivers a pretty robust performance per watt, while providing a significant return on investment for our customers. And largely speaking, for our AI on the edge customers, we have 22FDX. This is our silicon on insulator based platform that really offers unprecedented TOPS per watt with practically no leakage, and we'll dive into that a little bit more. So as I mentioned before, our FinFET platform is popular with those who are trying to optimize their return on investment for high performance computing, largely for cloud, but also cloud and edge servers for both training and inference. We have at least two customers who have gone public. One is Tenstorrent, which is showing just shy of 400 TOPS in 75-watt envelope, and Enflame has packaged 14 billion transistors in advanced 2.5D. On the edge side, where power is important, where you want to achieve very low leakage, very low power application, our SOI process is pretty beneficial to those who are looking at standard battery-driven integration. We have two customers who have come out in public. Perceive is talking about their silicon showing massive number of neural networks in a 20 milliwatt envelope with no external RAM. And Greenwaves is talking about 150 gigaops at just 0.33 milliwatts per gigaop, kind of a phenomenal set of numbers that they are able to achieve. So let's first dive into our FinFET platform. As some of you know, at GlobalFoundries, we were pursuing 7 nanometer development, and then we decided to do a pivot. And one of the interesting things we did was we brought some of our 7 nanometer know-how back to 12LP plus and provide that benefit to our customers. One of the unique things that we want to highlight is our SRAM. So, our SRAM is a pretty interesting innovation that we have done where, we basically allow for latching of four values. So obviously the latch may slow down the first access, but if there is a second or subsequent third and fourth access, then you avoid going back to the array for accessing it. And so a series of sequential reads can eliminate the penalty for the 3 out of the 4 accesses. And as you see, as a result, that results in significant savings for power. So the dual work function that we have, it enables, if you go compared to our 12LP, if you look at 12LP plus, you see significant benefit both in terms of your area and performance. On the top of that, what we also have is our DTCO offering, where our design analysis service, we work with customers. We are a specialty foundry, so we engage with our customers, help analyze their architecture, and then we help optimize the PPA through specialized offerings. And we'll show some of that in just a second here. So our 12LP plus is our dual work function gates. And as you see over here, when you have this as compared to your traditional high-K FinFET, the dual work function is basically providing you a pretty substantial benefit because of the reduced halos. We call it single dual. Some people call it dual and quad, but essentially your dual has 2N and 2P. And with the reduced halo implant, it allows you to achieve a variability, lower Vmin, and better mobility. And this is something that our customers see significant benefit in implementing their designs. Now, many of our AI customers have demanded that they want to focus on doing their research and their innovation on certain aspects of the architecture improvement or innovation they are doing, but to allow their route to market in a pretty rapid fashion, we provide a custom core reference package. So on the logic side, we have a logic library, which is optimized for AI. We provide optimized MAC units and other PP optimization, and then we enable their design analysis in various phases of their design. On the memory side, we briefly touched on our low voltage SRAM solutions, the low voltage bit cells, as well as the customized memory solutions that our customers find basically get to their tape out pretty rapidly and optimize for the AI needs. Now, to create your SoC, obviously you need a set of IPs beyond what your core ASIC function would achieve. And we work with many industry IP partners who have IPs that are validated on our process. What we show you here is a sample of the memory providers for DDR3 all the way up to HBM and HBM2E, our host CPU interface of PCI as well as USB. And then, we are working with multiple chip-to-chip, which is pretty heavy in demand with both parallel and serial or a combination. And then obviously, last but not the least, a standard cell and memory compiler players that we work with. The other thing I want to quickly show is, if we look at our competition, many of their process is pretty much optimized based on massive volume of mobile type of SoC, whereas at GlobalFoundries, our process is pretty well balanced, and we support a variety of customers. As you see over here, you have something like 10 to 15 square millimeter all the way up to approaching 700 plus with 20 billion transistors and everything in between. And this variety of largely high performance computing customers, it allows us to provide a balanced process so that we can cater to a variety of customers that are looking to produce all types of AI silicon and beyond. Now let's switch the gears a little bit to talk about our other platform offering, which is, we call it 22FDX. 22FDX continues to provide a significant innovation that we started some time ago on silicon on insulator. Fully depleted silicon on insulator essentially is a FinFET-like architecture, but the channel is extended, and this very thin channel and associated oxide, basically it provides a similar quality as FinFET. You get the fourth terminal, and this provides significant advantages from a power perspective, and we'll talk more about it. But this is something that we are pretty proud of, and you will see customers like Green Waves that or Perceive, they have announced some phenomenal results on their silicon, taking advantage of how we go beyond FinFET and the power and other benefits we provide to the customers. So in terms of what our customers get from us, obviously our FDX is the first industry's first and only body bias ecosystem that we have, and it almost provides very, very low leakage. You see here 1 picoampere per cell of ULL power option that we talk about. But we couple that with automotive grade IP, especially for MRAM, that our automotive customers find pretty helpful, and we'll talk a little bit more about it as well. But eMRAM is becoming an important element for many of our customers, because traditional SRAM is 6 transistors, as many of us know, but MRAM is one front-end capacitor and 1 transistor with magnetic material, and this especially is very good. The non-volatile nature is very good for our edge customers who want on and off and power savings and other features that they are looking for. Now, in terms of what we have done, we will show you some hard data over here. We first of all have worked with companies like Dolphin to prepare to prove our technology on their IPs, because you have to have drivers that regulate all of that good stuff. But what you see on the right side is, even if you don't use body bias, the baseline, as you go from 0.8 volt to 0.5 volt, you see a significant scaling in terms of advantage of speed, power, and leakage. And we would love to talk to customers in a one-on-one fashion, that if you enable body bias, then what sort of multiplicative benefit that they see on the top of what we show over here. But this is something that many customers are already seeing significant benefit out of. Now, we know that for analog circuits or analog compute in memory that Linley and others have talked about, stuff like ADC and DSC are pretty important. And our customers with AI on edge application, they benefit from us providing some samples. We provide some of these devices. And what you see over here on the right side for both ADC as well as DSC design, that as we look at and as we compare with our high-K metal gate, our 22FDX provides something to the tune of 20% area reduction, but between 40 to 50% power reduction. And this is something that we believe is ideally suited for IoT as well as other AI on the edge applications. Now, MRAM has been talked about a lot recently. Magnetic material base with two states. GF has chosen to optimize our MRAM. MRAM you can optimize for two purposes, right? You can optimize it for either storage, or you can optimize it for a write function. We have chosen to optimize it for storage purpose, because AI customers are demanding it pretty heavily. But if you look at where this is coming to of significant benefit, if you look at our IoT customers who are demanding fast on and off, then this ultra efficient, power efficient eMRAM subsystem is of significant benefit. But as we look at the overall edge ecosystem of IoT and beyond, then customers are asking for connectivity, energy efficiency, reliability, as well as automotive applications are looking for ADAS and self-driving as very specific set of demands that they have, and our 22FDX is a pretty popular platform for that. One other thing I want to mention is as industry is evolving, Linley touched on it in his keynote this morning, that the models are getting huge as time goes forward, and ability to address those large models with just pure scaling is becoming impossible. And Linley talked about big and little core and all other variants. We have customers who are either already exploring architecture innovations with chiplets type of approach, where you have 2.5D, 3D along with a die-to-die interconnect. And we have some interesting things that we offer in terms of chip-to-chip or die-to-die implementation, along with our multi-dimensional packaging and our work on interposer, as well as our working with OSAT for rapidly assemble and test. This is becoming very important as people try to innovate beyond what the scaling just provides, as they disintegrate and then do the packaging. And we also heard from Intel recently that they are taking their EMIB or co-EMIB as well as the 3D packaging to the next level of innovation. And we believe industry is going to innovate more in this space. Last but not the least, we know that no one size fits all. The optimal computing architecture of future is going to vary by the workload. We are pretty proud to partner with some of the customers who have gone public with their silicon announcements, Enflame, Tenstorrent, Greenwaves, and Perceive. What you see on the right side are the customers, primarily targeting the cloud inference and or training workloads. And what you see on the left are the edge AI customers leveraging our 22FDX. So with that, Mike, we could potentially open up for some questions.
Okay, Hiren?
Yeah,
just reconnect here. Just reconnect me here. Okay, great. Thanks. That was an interesting talk. I had a question. You described the SRAM technology and the 4-to-1, excuse me, the 4-to-1 mux. Is that used to access 4 consecutive values, say, for convolution? How is that typically used?
Yeah, so in a traditional domain, Mike, when you want to do sequential access, then you are going back and paying the price, the penalty, because you are accessing back in the array. Having the storage element in between, as we discussed, and I might just even flip that to that page to quickly show that picture. But essentially, by having that storage in between, now when the next sequential element, because you are preserving 4 in the storage element in between in the latch, as you see over here. So after you read the first one, when the second sequential need comes through, then you don't have to pay the penalty of going back to the storage element all the way into the array, but you have that available in the latch, so you can rapidly access it. So in the traditional compute SRAM, you paid a lot of penalty for going back and accessing the array, whereas out here, you have this thing available right in the latch.
So you would load it every 5th cycle, say?
There is a continuous load, correct, into the latch, yes.
Okay. You go ahead and stop sharing your screen now, and we'll just go through some of the audience questions. The question on the SRAM. The SRAM that was optimized for AI in the 12LP plus, is it backward compatible with the 12LP node?
Our 12 and 12LP plus entire library, all the things we offer are backward compatible. So for customers to move from 12 to 12LP plus is pretty rapid. We have added things, but the backward compatibility is preserved, yes. We would love to talk to customer in more detail on that one. This is something that customers are pretty excited about. You are essentially getting the benefit of innovation done for 7 back into 12. So the return on investment for customers is amazing. Great.
Then a question on the MRAM. How does the area of a MRAM cell compare to a 6-transistor SRAM?
Okay, so I think the SRAM that we was on the 12LP plus, the MRAM we talked about it, but generally speaking, the density is about 2x.
Okay.
MRAM is 2x smaller.
And then, okay. Question on whether you offer a multi-project wafer service or low-cost shuttles for 22FDX.
The short answer is yes, but we would reserve the right to work with each customer on a case-by-case basis. But we do this every other month. And we engage with customers on a need basis, especially in 22FDX, which is hugely popular. with a wide swath of AI. So the short answer is yes, but we'll work with customer on a case-by-case. On 12LP Plus, we do it once a quarter.
Okay. I think this next question would be on a case-by-case basis as well. The question was on the cost differential from 22FDX to 12LP, or in terms of what the area shrinkage would be from 22 to 12.
Yeah, so I think it depends on the application that you're talking about and your implementation and all of that. I think a specific answer to this, we would look at your situation and let's talk one-on-one. I think there are generic numbers we can share, but I think this is one of those things, and we're going to have opportunity to have one-on-one, and we can do a little deeper dive into that the topic. Plug for setting up one-on-one.
Sounds good. And then talk about MRAM, and you also mentioned that you optimize that for storage, but I think you also mentioned its potential use for in-memory computing, which Linley briefly talked about this morning. Would you need to do some different type of optimization to use an MRAM cell for analog computing?
So first of all, the MRAM can be optimized for two purposes, right? It can be optimized for flash, eFlash purposes, which is what we have chosen to do in 22FDX, or you can optimize it for S, or we call it MRAM S, for SRAM replacement. And the customers that we have today are largely using it for weight storage already, because that's what the demand is, and that's what we chose to do it in 22FDX. So that's what our focus is right now.
Okay. We've heard a lot about in-memory computing, their potential, but it seems to be slow coming to market. Is variability the issue there?
So first of all, analog memory, in-memory compute, or ACIM as the acronym goes, we have multiple customers that we are engaged with in different stages. I think things are way beyond the architecture, things are way beyond implementation, things are in design or test. So I will stop at that. We have ENVM with multi levels that we have in development that customers find pretty useful going forward as well. But yeah, we'll answer more questions on a customer by customer basis. We are pretty excited about in-memory compute, by the way. We have multiple customers that we are engaged with.
Good. Yeah, it's an interesting new approach. There's a question on, are any of your automotive customers, have they publicly disclosed that they're using your technology for MRAM?
There is one customer, and I'm forgetting the name, out of Israel that has done a specific development. But Mike, as a foundry, we basically, I think the name of the company is ARB. I hope I'm pronouncing it right, ARBE. They are out of Israel, and they have made a public announcement. But as a foundry, we don't go pre-announce what our customers are doing, and I would just leave it at that. Obviously, we have a challenge where we may have 50 customers, but only 10 may choose to go public. But under NDA, we can have more discussion.